a very interesting one because we are going to have a lecture from a reputable fellow. It's at this point that I will say, though I'm not worthy to untie the ropes of your sandals, but permit me, sir. Our speaker for today is Mr. Jerry Chechet Kahu. So I'm just going to read his profile. He's a principal regulatory officer at the National Agency for Food and Drug Administration and Control, NAFDAC, with more than 10 years experience in food laboratory analytical testing. He has a bachelor's degree in biochemistry and a master's degree in nutrition from the prestigious Ahmadu Bello University, Zaria. Jerry's expertise is in the field of food quality and safety, with high proficiency in instrument operations such as HPLC, LC-MSMS, GC-MSMS, and FTIR. He's also very experienced in ISO 17025 for testing laboratories, current good manufacturing practices, and food facility inspections. Jerry is an advocate of food security and has dedicated his career towards ensuring consumer protection. He is a member of the Nigerian Institute for Food Science and Technology, NIFT, and also an associate member of the Royal Society of Chemistry, United Kingdom, RIC. Mr. Jerry, it's so nice to have you talk to us today. This is a very wonderful profile. So I think Jerry will take over from now.
Okay, thank you very much, Nena, for this introduction. So I'm going to quickly share my screen. Okay. All right, you're welcome to today's training. Our topic for today is food contaminants, regulation and standard analytical methods of key chemical contaminants in food matrices. So let's start immediately with the outline for today's training. We are going to discuss some definitions, talk about different food contaminants, then we'll talk about the standards and the regulations. Then we'll now conclude with the analytical methods required for testing of food contaminants. What's food safety? Food should be safe for human consumption and free from hazards that may compromise the health of the consumer. We as food scientists, our paramount duty is to ensure that food are of good quality and are safe for human consumption. That's why here it's referred to, food safety is referred to as the practice and conditions that preserve the quality of food to prevent contamination and foodborne illnesses during preparation, handling, and storage. There's a key here. There must be no acceptable health risks to food. So food safety is a key and fundamental part or pillars of food security. And for us to ensure food security in Nigeria or in the world, we need to ensure that our food is safe as possible. I know it's sometimes difficult to eliminate the risks or hazard completely, but our goal is to be able to reduce the risks as low as possible. What are food contaminants? Food safety largely involves food contamination. Food contamination happens when something gets into the food that shouldn't be there. Anything going into your food, it can be anything that is not a nutrient or something that might cause any harm. It's then food contamination. So here we can see that food contamination is defined as any substance not intentionally added to food. This can come from on-farm production, from manufacturing, from processing, packaging, and storage. So you can see that it cuts across the agricultural and food value chain. So at every step, it is necessary that food is being monitored for safety. Every step of our value chain, food must be monitored for safety. So here we classify food contaminants based on two criteria: the way and when they enter the food production chain. The first one, it's primary contaminants. These are contaminants that come into the food through an external source. Anything that goes into your food that becomes a hazard, not produced within the food, is a primary contaminant. So those things can be your metal, sand, it can be pesticides, or any chemical that comes into the food, either during on-farm production or during processing. It might be as a result of the machines or equipment you're using, you have contaminants coming. It can be as a result of the food packaging material you're using. So those contaminants can migrate from the package to the food. So all these are termed primary contaminants. Then the second one is secondary contaminants. These are contaminants that are produced within the food. they are not coming from external sources. They are internal. So there are things that facilitate the production of these secondary metabolites. So when those things are produced, we call them secondary metabolites. And in other terms, I like to define primary contaminants as toxicants, while your secondary contaminants as toxins. Then we have categories of food contaminants. There are two. First is the naturally occurring contaminants. These are produced by living organisms. So you can see that these naturally occurring contaminants can also look as or behave as the secondary contaminants. They include phytotoxins, and these phytotoxins, they are poisonous substances that are produced by plants or plant pathogens with bioactive properties. They are very harmful to the body. They cause some toxicological effects to both animals and humans. While you can see examples, we have antinutrients, we have glycoalkaloids. Then the second example of a natural occurring contaminant is mycotoxins. Mycotoxins, as we know, they are toxic chemicals produced by fungi. These contaminants, these mycotoxins, they are strictly produced by fungi. So here, sometimes it's been said that while not all mycotoxins are from fungi, but not from fungal origin, let's say, not all toxins compounds produced by fungi origin are mycotoxins. So it means that all mycotoxins are produced by fungi origin organisms. Then the third one, it's phycotoxins. Phycotoxins are natural contaminants that are produced by algae. These contaminants include ciguatoxins, we have saxitoxins, we have diuretic shellfish poisons. All these contaminants are very harmful to the body. So it's really paramount for us to monitor and regulate these contaminants. Then the second category is the non-naturally occurring contaminants. This includes your agrochemicals, pesticides, heavy metals, organic, these persistent organic pollutants, polycyclic aromatic hydrocarbons, veterinary drugs, sand, hair, all those physical contaminants. Then we go to types of food contaminants. Food contaminants are divided into three types: the physical, chemical, and microbiological. The physical, we can see we have things like metal fillings, glass, insects, sand, hair. Chemicals, we have pesticides, vet drugs, mycotoxins, POPs. Microbiological, we have bacteria, fungi, viruses, and parasites. Then for the scope of this training, we are covering only chemical contaminants. For the chemical contaminants of interest, we are going to cover mycotoxins, we're going to cover pesticides, we're going to cover heavy metals. So what are mycotoxins? Mycotoxins, these are toxic chemical products produced by fungi. They can grow on crops. They can grow during pre-harvest or post-harvest. In the farm, those fungi can grow on our crop products. After post-harvest, during storage and handling, those fungi can also grow. These mycotoxins, they are very small molecules, which is less than 1,000 daltons. They are very small. They are one of the critical aspects of this mycotoxin is they are not biodegradable, which is a very big issue. This has raised a lot of food safety concern because when a chemical is not biodegradable, it's not easily taken out from the environment. It's not easily taken out from our food. So you can see that they will always persist in those food. So this is the issue that is attached to these mycotoxins that we're having. They are also resistant to heat, highly resistant to heat. They are resistant to freezing. They are resistant to food processing. It means that if you have a maize product that is being contaminated with mycotoxins, no matter how you process that food, no matter what cooking method you've employed, it's very difficult to eliminate those toxins. Those toxins stand the test of time. So it's paramount we prevent our food products from being contaminated with these toxins. Because once they are contaminated, it's difficult to take them out. Currently, we have over 300 known mycotoxins that are available. So we are going to look at some common mycotoxins of interest that affect our environment here. Let's say Nigeria, West Africa, Sub-Saharan Africa, mostly, and even the world, yeah. But in Nigeria, there are some that are of high interest due to the products we consume and produce. So the first one is aflatoxins. aflatoxins are produced by Aspergillus flavus and Aspergillus parasiticus. Currently, we have over 30 aflatoxins available, but the main ones are aflatoxin B1, B2, G1, and G2. These aflatoxins B1, B2, G1, and G2 are classified based on their fluorescence nature under UV light. And the B1 and the B2, they fluorescence blue, while the G1 and G2 fluorescence green. So that's why they were termed B1, B2, G1, and G2. And also for their chromatographic mobility in thin layer chromatography. Then we also have aflatoxin B1, M1, and M2. So from the diagram here, you can see that these aflatoxins are mostly polycyclic compounds. So they have alternating single and double bonds. And that will also help when it comes to their dictation or the analytical method we're going to use to analyze these toxins. Aflatoxins are mostly carcinogenic. They affect the liver. They can be hepatotoxic. They can be some reason for hepatitis. And it's not something that once you consume an aflatoxin today, by tomorrow you have cancer. No, it has a chronic effect. It takes time. It builds up. So it's something that it will take you maybe a long time to not develop this sickness. So you might be wondering, how did I get this? This is a chronic effect of the consumption of these toxins. B1, aflatoxin B1 is the most potent carcinogen as of today. It's highly carcinogenic. So it's something that analysts and food scientists today are always analyzing, trying to make sure that this B1 especially are not seen in our food products. Then the next mycotoxin, it's the okra toxins, which are produced by Aspergillus ocraceus and Penicillium verrucosum. These okra toxins are divided into three. We have okra toxin A, B, and C. You can also see from the structure, they are also polycyclic compounds. And okra toxin A remains the single most potent member of this group of mycotoxins with a very long half-life in humans. So you can see something that has a long half-life can be very difficult to eliminate. So it's paramount for us to also make sure we do not have these toxins in our food. Okra toxin A is a potent nephrotoxin and represents hepatotoxic, teratogenic, and immunotoxin effects. Then we have some other common mycotoxins, which are not mostly researched in this part of the world, but of recent, I think there are more research works that are coming out on fuminosins and the oxynivalenon, which we call DON. Then some other ones are zearalenone, ergot alkaloids, patulin, and citrulline. How does mycotoxin occur? We have the primary contamination in its occurrence, which can be seen in products like cereals, nuts, spices, and fruits. Examples, we have wheat, maize, figs, and the rest. Yeah, these are primary contamination. You see mold or fungi growing in your maize product, for instance, in the picture we're using here. It will be very certain that, or there's a high probability that these fungi are going to produce these toxins because there are certain conditions that favor the production of these toxins while fungi grows. So these are what we call primary contamination. And this contamination, specifically for aflatoxins, covers what we call the B1, B2, the G1, and the G2. Then you can see that sometimes what people do, especially those manufacturers, they'll see a maize product that has fungi or mold. Then they'll say, oh, humans, we cannot consume this thing, but let's give it to our animals. So they now process these products with the mold and fungi and the toxins that have already been created or produced in those products, in those maize products. They will now process it and now produce feeds, animal feeds. So once they produce animal feeds, they feed it to chickens and all such. And we'll now say, oh, that's all. The aflatoxin that is here, or the mycotoxin has been eliminated. It has not. Once these animals feed on these such feeds, those products, remember we said they are non-biodegradable and they're very resistant to processing. So obviously it's going to be in the feed. And once it's in the feed, the animals will consume. It will bioaccumulate in the animal. And if it bioaccumulates in the animal, you can now end up seeing it in the meat of the animal or in the animal products. If, for instance, for chickens now, you might be seeing it in the egg, of that chicken. In cows, you see them in milk and cheese and all such. So, but they don't come out as aflatoxin A1, aflatoxin B1, B2, and so it comes out in a different form. There's some derivatives that have been produced. So that's where you see this kind of indirect contaminations produce aflatoxin M1 and M2. So M1 and M2 are gotten from milk, cheese, meat, egg, and the rest, animal products. So any of such products should be discarded and destroyed. Then what are the types and hosts for mycotoxins? You can say aflatoxins can be seen in peanuts, maize, dry figs. Fuminosins are only found in maize. Ochratoxin A are found in cereals, dry fruits, wine, coffee, tea. The oxynivalenol are found in cereals. Butylene is found in apple juice and other fruits. Then what factors are responsible for mycotoxin production? High humidity, over 70%. It favors the production of fungi, mold, then subsequently production of mycotoxins. High temperature, over 30. The moisture content of the crops. If you don't dry these products properly, yeah, that's why we are encouraged to dry our products very, very well. So in that aspect, if you dry your products to a certain moisture level, it's easier it's very difficult for microorganisms to grow. So if microorganisms are not growing, it's difficult for mold, fungi to grow, and hence you limit the level of mycotoxins in these products. Then insect infestation can also be another factor. Then large carbon source. So if you notice, most of these products are carbohydrate dense products. Then we go into pesticides. Pesticides are chemicals that are designed to prevent, destroy, reduce pests of any such. They can also be called plant protection products. And these pesticides include many kinds of ingredients used in products such as insecticides, fungicides, herbicides, rodenticides, repellents, weed killers, biocides, and plant growth regulators. So I know fumigating our farm, it's very important. Yeah, it's important, especially when your farm is being ravaged by pests and insects and weeds. So it's easier to fumigate to eliminate those threats. But also keep in mind that once those products are being, or those farm produce are being fumigated during production or during storage, a certain amount of those actives, of those fumigants or pesticides that remain in the food matrix. So with that, it will become a risk. So we have certain groups of pesticides that we are going to cover. So the pesticides are divided into 5 major groups. Firstly is the organochlorines. The organochlorines are groups of chlorinated compounds that are widely used in the production of these pesticides, and they are very persistent in the environment. These organochlorines have high chlorine-dense compounds in them. We can see examples: aldrin, we can see heptachlor. These are popular pesticides that we see in the market. Then the second one is organophosphates. Organophosphates are compounds that have a central phosphate molecule with an alkyl or an aromatic substrate. So you mostly see aromatic backbone structure or an alkyl backbone structure, but with a phosphate molecule, a central phosphate molecule. So the examples of them are parathions, diclovos. Diclovos is one of the most popular organophosphate that is used here in Nigeria, and it's used widely. It's widely used, and I think you might know it from this popular fumigant, Sniper. That's the active ingredient of Sniper. So you notice people. There was a trend one period that farmers were using Sniper to preserve beans, which is true. They were doing that so that all those pests, insects, and all such will not attack the beans. So, but it takes time for these pesticides to be eliminated from the product. So, what they do, all those farmers do is that they will now spray these pesticides on their storage products. Then today you have bags, let's say 50 bags of beans that are stored, you have already sprayed so that insects will not come. Then next day, someone will call you, there's a market too. Someone is looking for 30 bags and is offering this amount. You are supposed to allow these products to stay for the required time period before being sold for consumption. But no, because of greed, they will sell it. And once they sell it, it goes to the market, people start buying and people start eating, and it starts affecting the population. So this is some of the safety issues that we normally see in our agricultural markets today. Then thirdly, we look at carbamates. Carbamates are organic compounds derived from carbonic acid. So these carbamates, organophosphates and organochlorines, they work by damaging a particular enzyme in the organism, which is acetylcholinesterase. So once they damage this enzyme, the enzyme normally is responsible, or let me just say it's critical for controlling nerve signals in the body. So once these things are damaged, you will now see that the pests or the insects you're doing will die. Well, at the same time, if we eat some of these pesticides, we consume them, they are also associated side effects that will affect humans. Then the last two, we have the peritrins and the pyrethroids. Those ones are derived from ketoalcoholic esters of pyretroic acids. They are what these peritrins do normally is they affect the sodium channels in the organism, thereby leading to paralysis of the organism. Then we have our polar pesticides, which are highly ionic and they are very soluble in water and with little solubility in organic solvent. And because of that, once it comes to analysis of polar pesticide, it's very, very difficult. It's one of the most difficult pesticides to analyze. So there are currently people are developing methods and validating methods for the analysis of polar pesticides, which has to require the use of LC-MSMS. So we'll now look at pesticide residues. We discussed these are pesticides. Then pesticide residues, they are the active ingredients of these pesticides or metabolites that remain in the food. So once you spray, anything that remains in the food permanently is termed your pesticide residue. They can also be derivatives or degradation and conversion products. They can be impurities, reaction products, or they have to be considered to be of toxicological significance. Then veterinary drug residues. We know vet drugs, they are intended for diagnosis, for cure, for treatment, and prevention of diseases in animals. They apply to keep animals healthy. They also enhance growth, but they also have their side effects. So the residues of these veterinary drugs, we have some of these veterinary drugs include penicillin. You can see metronidazole. These are widely used in poultry farms. So once you have these residues in the body, in the animal, the animal is you're already getting meat from the animal. You're getting the animal products, and these residues of these vet drugs can remain in those animal products. So once they are in the animal products and we as humans consume these products, you will now see that the concentration might be a little bit small. And if the human is already having some parasites or microorganisms that these drugs usually fight against, what happens is that because of the low dosage of the drug in the food, you now consume that food. The drug will definitely want to fight off these parasites or microorganisms. But because the drug is at a very low dosage that comes from the food, the microorganisms will create a defense mechanism because the drug will not be able to kill most of them. So it's going to create that resistance to the drug. So continuous consumption of these products create a longer resistance. So that's why you now be seeing things like drug resistance and antimicrobial resistance. So these are some of the issues that we face consuming some of our animal products which contain levels of these drug residues. Then heavy metals, they are metallic elements with high density. It's toxic at low concentration. So we have some examples: mercury, lead, arsenic, cadmium. You can see cadmium is responsible for respiratory issues. Even arsenic is carcinogenic and also. So these heavy metals, we are also meant to be reduced or eliminated in our food. Then what's the purpose of food testing? First is to ensure compliance with food laws. We have to, for you to test the food for contaminants, we have to ensure that why we're doing that is to make sure we comply with the law. There are laws and regulations that have been placed for every food contaminant. So we test to ensure that there's a compliance with that regulation or laws that have been placed. And secondly, to secure access to import and export markets. Obviously, if your food is being contaminated, there will be a market difficulty. That you have high difficulty in exporting those products, or even for local consumption, because the regulatory authorities are definitely going to clamp you down. And if you're exporting the products, the importing countries are going to hold the products and ban once the test and the products have been contaminated, or the levels of these contaminants exceed the residue or the maximum limits. So I think currently, recently we have, it's not of recent really, it's been trending for a while. we have issues with the European Commission. Most of the European countries do not take beans and some greens from Nigeria due to high levels of pesticide residues. And there are a lot of issues affecting that because, yeah, there are foods that come to regulatory agencies like NAFDAC and they are being tested, having low levels of residues, being approved. Then you still have people that are smuggling those foods out for exportations. And once they get to those importing countries, they collect all those foods and take them to the lab for testing, and they discovered those foods have high pesticide residues. So they had to place a ban on Nigeria. So that's why they say for us to fight food or to tackle food safety, it has to be a collaborative effort between different agencies ranging from the private sectors to the government sectors. Then last is to protect customers. Our consumers, we have to ensure that the food they are eating are of good quality first and are safe for consumption. Then what are the food standards? Food standards is a set of criteria that the food must meet if it is to be suitable for human consumption, such as source, composition, appearance, permissible additives, and the maximum bacterial content, while regulations are the legal rules that are issued by government agencies or regulatory authorities in order to implement the various food safety and food hygienic procedures as to achieve assurance of good and consumable quality of the products. We can see some schemes and standards of food safety. We have the pyramid here. The first one is the market requirement. This market requirement, it's drafted by organizations such as the Global Food Safety Initiative. These are private schemes. There are market requirements for the food you are sending to the local market or the open market or the ones you are exporting. Then we have voluntary standards that are being created by International Organization of Standardization and their Association of Official Analytical Chemists. These voluntary standards are mainly for analytical methods, for method validation, for laboratory accreditation, for GMP, and for quality management system. These are voluntary standards. These standards are there. It's left for you to follow them. So it's not something they make it mandatory that you must do this. So it's left for you as either a regulatory agency or a manufacturer to follow these voluntary standards. Then we have those that are mandatory. These are the national, international, and regional regulations. So we can see that we have things like the maximum residue limits, quality, hygiene. All these are mandatory standards and regulations that must be followed. If, for instance, we are using dichlorobos as a case study, and they say dichlorobos in your beans should not be more than 0.01 ppb. Now, this is a regulatory standard that has been placed. So you cannot say, I want to decide not to follow that standard because I find after testing that my dichlorobos is at 0.05. So I can decide not to follow. No, there are limits, there are regulations that must be followed because these have already gone through risk assessment. Then we have other voluntary standards are Codex and the World Trade Organization. So here we look at for some regulations driving analytical requirements. So for analytical requirements, the first one here, you can see a Codex Alimentarius Commission guideline. On the top part, that guideline is on performance criteria for method of analysis for the determination of pesticide residues in food and in feed. That was adopted in 2017. This guideline is for testing laboratories. If you are involved in pesticide and pesticide residue analysis, these guidelines must be followed. Because for you to have a method, even though that method might be coming from an official reference compendium, you have to follow the guidelines for that method to make sure that that method is fit for purpose. So you can have a method in a compendium that was generated somewhere else. Now you have your local laboratory and you have the instrument to analyze those contaminants or those pesticides. So I cannot just pick a method from the compendium and use it for the first time, then get my result, then start confirming or asserting that results for use so that those products can now be taken to the market or for export. You have to do something first. You have to validate that method. So that method must undergo validation and verification. So for you to validate, there are certain performance criteria that are in place. So once those performance criteria are there, you now run through your analysis, validate that method using the criteria. The criteria examples of those criteria are accuracy. You have to find the accuracy, find the precision, find the bias, the robustness, the limit of detection, the limit of quantification, and so on. Recovery. So you have to make sure that the method you are taking from the compendium, your instrument can adopt that method and do it very well. So once you validate the method and it has checked all the criteria, then you can now say this method is fit for purpose in the lab, and you now adopt it in the laboratory. So this is what we call, these are part of the regulations we have. And there's one coming, the same method validation procedures coming from European Commission. So you have one from Codex, you have one from European Commission, which is a scientific guideline. I think it was generated in December 2020 and was adopted in January 2021. So this is also similar methods for method validation for pesticide residue analysis. Then we can see we have the ISO 17025. This is a requirement for the competency of testing and calibration laboratories. So especially you want your laboratory to be accredited, this is the guideline to follow. It has everything involved in laboratory accreditation. So once you follow this guideline, it's easy for you to get accredited for your laboratory. So you can see we have AOAC, we have the one from FDA for milk drug residues. So these are some regulations that can be followed. Then analytical methods for food contaminants. Yeah, for the purpose of this training, we are going to look at these methods. First is the lateral flow device, then enzyme-linked immunosorbent assay, high-performance liquid chromatography, gas chromatography mass spectrometry, liquid chromatography mass spectrometry, atomic absorption spectrometry, then finally inductively coupled plasma optical emission spectrometry. Don't worry, I'm going to explain them properly as we go on. So the first one is the lateral flow devices. These lateral flow devices are common point of care diagnostic tools. They are paper-based technology used for detection and quantification of analytes in complex mixtures. So if you have done this hepatitis, rapid hepatitis test or HIV test, you see those strips that are being used. These are lateral flow devices. So the LFD use the interaction between antibody and antigen to detect the presence of an antigen in a liquid. So here, if we talk about antigen, we are referring to our analyte of interest. The lateral flow device currently is for food contaminants is used in analysis of mycotoxins. So for aflatoxins, for DON, for ochratoxins, and the rest. So FLD is composed of the following elements: sample pad, we have the conjugated release pad, membrane, and then adsorbent pad. So I'm going to show you a principle. This is a pictorial principle of FLD, how it operates. So you can see from the left-hand side, you see the sample pad. The sample pad, this is just where you put your sample. So once you've done your sample preparation, you've done the extraction of the sample in a appropriate solvent, then you come here and insert the sample in the sample pad. So once the sample goes, the sample contains the analyte of interest, which is our antigen. So once you put the sample into the sample pad, the sample has a filter. It even filters the sample itself to reduce some of those matrix effects that might come from other compounds that are within the sample. Definitely, it's not just your aflatoxin, for instance, that is within the sample. If you're running a test for aflatoxin, it's not just aflatoxin that is in the sample after extraction. There are so many other compounds. So, but the filter will also help in reducing those, sieving out some of those things and reduce the matrix effects to ensure accuracy of your results. So once you've placed it in the sample pad, the liquid, it's a liquid, it will now flow to the conjugated pad here. So this is a conjugated release pad. What this pad has, the conjugated release pad, you can see this red thing there. It represents, it's what we call a conjugated antibody. I remember I said it's like this LFD is an immunoassay. That means it's an interaction between antibody and antigen. So the conjugated pad contains the antibody, while your sample has the antigen of interest. So once the sample flows to the conjugated pad, it now interacts, it now binds with the antibody. So the antibody and the antigen binds together. Then they now flow to the other parts where you see the NC membrane. The NC membrane is a nitrocellulose membrane. It contains the test line and the control line. So in that NC membrane, as the sample moves along the membrane, there's a binding reagent that is situated on the membrane that will bind to the target on the test line. The target is our antigen or the analyte of interest. So that binding reagent that is in this test line will now bind to our conjugated antigen and antibody. So once it binds, then there will be a color change. Most of the time, the color change is red. So it will now change. So once it changed, it has now signified that the antigen of interest is present in that sample. So you can use this lateral flow device as a qualitative method of analysis or screening method. Then it can also be used for quantitative. So once it has signaled, okay, yeah, the antigen of interest is there, all the solvent will now flow down to the adsorbent part. The adsorbent part is just to absorb the liquid that has run through the strip. So once you do that, you've identified that, okay, the aflatoxin is present. Then in some methods, you can also quantify. So in this part, we have LFD that is from R Biofarm, Germany. I've used this one of recent. Look at it here. Below, you can see there's something like a barcode, like a cover with a barcode. And after that, that strip is the lateral flow device. So there, the sample pad is there. You can see visibly the membrane. That's a nitrocellulose membrane where the color chain might appear. So this is an example of an LFD from R Biofarm for aflatoxin testing. Then what are advantages and disadvantages of LFD? One, the advantages: it's user-friendly. It requires less training. It's very easy to use. It's a rapid test. It's not expensive as compared to all those instruments like your HPLC, your LC-MS. It's cheap and stable. Then it can also be used in the field. That means you just don't have to be in the lab. So if there's a survey work you're trying to do that you need to go to the farm or to go to storage sites, you can actually take your LFD device. It comes in a box with everything, all the things that are necessary for analysis. You go to the field, analyze the product on site. So you also have to, it's not necessary you bring the products to the lab and analyze. Something you can do there in the field. It's very fast. Everything with the sample preparation and analysis will not take you more than 7 minutes. So you can see it's actually fast. Then it can also be used for quantitative analysis. So let me just go back here, like this one that has this strip. You can see this barcode. This method, we use a phone. There's the mobile phone comes with the app. So you now scan the barcode, register it. Once you've inserted your sample, you cover and incubate. So it will now run through. If there's an analyte of interest, it will signal with the red line. Once you are done, you now cover. Then use the phone, that app with the phone. You now scan through. Then the app will quantify the amount of mycotoxin, amount of aflatoxin in that sample. So you can see it can be used for quantitative analysis, but the disadvantage is that it's not reproducible. The reproducibility can be a problem. That means you can use it here in Kaduna, and I'll now take it to Enugu, and it will not work. I'll take it to Lagos. The results will vary, so that reproducibility can be a problem. Then the sample, since it does not involve a lot of cleanup, you understand, and you are not using all those instruments like your tandem mass spectrometer, the interferences can occur from the matrix because of the other compounds that are there in the matrix. They can interfere with the results, and the result might not be as much accurate. But that's why we call it a screening method. It's not a reference method that should be used. Then ELISA. The ELISA is enzyme-linked immunosorbent assay. It's an immunological assay commonly used in measures of antibodies, antigens, proteins, and glycogen. You can see this ELISA method. This ELISA method is also a bit similar to the LFD method because it also involves the antigen and antibody interaction. So here, ELISA uses either an antibody or an antigen, which has an enzyme. So the difference is that ELISA has an enzyme linked, and a substrate will also react with the enzyme to produce a color product. And there are 4 types of ELISA. We have the direct, indirect, competitive, and sandwich. Sandwich is the one that we commonly use here, or is even commonly used in the world here. So this is some analytical steps for ELISA. So from here, let me just run through this from the left-hand side. You can see where you have the antibody that binds to the well. So here, what happens is that you put a capture antibody into the wells. These 96 wells are there. It's a plate, it's a microplate. So you now first insert the appropriate volume of your capture antibodies. So once it's inserted in the plate, then you now add your sample. You have to prepare your sample, do the extraction. centrifuge, get a clear solution, then you now add the appropriate amount of the sample to the well. You know, the sample, I said, contains the analyte of interest, which is the antigen. So once you add that, the antigen and the capture antibody you've added previously will now bind. So once they bind, then the next step is to wash the microplate. You want to wash it with distilled water. So once the essence of washing this plate is to remove unbound materials, thereby just leaving the antigen of interest. Because you know you have other, as we say, the sample contains other compounds. So once the antigen of interest are bounded to the antibody, then any other thing that's there, you wash it away with water. So once you've washed it away, then you now add the second antibody. The second antibody is what we call the detection antibody, which is also called enzyme conjugated antibody. So that's where the enzyme linked is coming from, the name ELISA. So once you add the enzyme conjugated antibody, it binds to another site of what? Your antigen. That's your analyte of interest. So you will see that your analyte of interest has two antibodies binded to it. First, the capture antibody that captures it. The capture is just to capture the antigen of interest so that you'll be able to wash all the other analytes that are not of interest. Then the detection antibody, which is the enzyme conjugated antibody, will now attach to what the capture antibody has captured. It's not attached to the antigen, or we call it the analyte of interest. So once it attached, then you can now proceed to wash it again. You are now washing the microplate to now remove the unbounded antibodies from the unbounded antibodies, leaving only those that are specific to the target of interest or the analyte of interest. So now you know you've added the enzyme linked conjugated antibodies. So wash it off. So any antibody that is there that is not attached to the analyte, let's say aflatoxin, then that one will be washed away. So if that is washed away, then you now proceed to the next step to add the substrate. So you know it's an enzyme already. The antibody you added the last time, it's an enzyme link, so it's an enzyme. So you now add the substrate. The substrate is converted by the enzyme on the detection antibody, producing a color change. So once you add the substrate, you now see color change. So if there is aflatoxin, you see the color change. If there's no aflatoxin, that means nothing has been captured, nothing has been detected. So you will not see any color change. So once you've seen the color change, you now insert it in the reader. You use the reader to read it, and it will now calculate your results. So this is like a classical step of ELISA analysis. So let's proceed to chromatography. Chromatography is a technique that separates the compounds in a mixture. So from the word chromatography, from the first time, it means separation of colors. So the technique is adopted to separate analytes. So I have a mixture of 3 analytes, A, B, C. I can use chromatography to separate all 3. So, and separation can be based on affinity, can be based on charge, hydrophobicity, and size. So if you look at this place, solutions, if you have solutions, you can use liquid chromatography, ion exchange, or thin layer. If you have suspension, you can use size exclusion chromatography for the separation. If you have gases, you can use gas chromatography. Then liquid chromatography, or in other words, your high performance liquid chromatography, HPLC. Most LCs or liquid chromatography applications for food contaminants analysis use affinity separation. Okay, so before I continue, for our LFD and ELISA, let's take note. It's used for the analysis of mycotoxins, aflatoxins, ochratoxins, fuminogens. Okay, yeah, it's not used for pesticide residue or for veterinary drug residue or for heavy metals. So now liquid chromatography separates based on polarity. How polar? You know, there's this term they use in polarity. They say like for like. So if you have a polar and polar, 2 of them will attract to each other. Non-polar and non-polar will attract to each other. So for liquid chromatography, the separation is based on polarity. And that polarity is determined by what? Your stationary phase. So if your stationary phase in your LC is non-polar, that means analytes that are non-polar will be attached more to your stationary phase, while those that are polar will be eluted out of your stationary phase faster as compared to those that are non-polar. So there's an attraction for like for like. So liquid chromatography uses 2 phases. One, the mobile phase, then stationary phase. The mobile phase is a solvent that carries the sample or the analytes and run through the column. The column contains the stationary phase. So it runs through the column in an isocratic or gradient run for separation. So once we say isocratic, what we mean is I have my mobile phase mixture. Let's say I'm using 50% of methanol and 50% of water as my mobile phase. So if I design my method, I'm going to be running for that analysis. I'm going to use 50% methanol, 50% water as my mobile phase throughout the run. So that is an isocratic run, because the composition of your mobile phase does not change within the run. But for gradient, the gradient, I can start up, let's say my run is for 10 minutes. I can start up 1 to 5 minutes, use 50% of methanol and 50% of water. Then from 5 to 8 minutes, use 70% methanol and 30% of water. Then for the 8 to 10 minutes, then use 50 and 50 again. So you see within the run, the composition of your mobile phase has changed. So that is a gradient. Gradients sometimes are used when you're working on multi-analytes. You have mixtures of different analytes. Like now I'm working on mycotoxin mycotoxin B1, B2, G1, and G2 in the same. I want to analyze all of them in the sample. So now all of them will separate in one chromatographic run. But maybe one of the aflatoxin is eluting, coming out maybe around 15 minutes. So I don't have the solvent to be running for 15 minutes. So I can do a gradient. That gradient will now shift that last one and come back to the time I want it to. So that's the advantage of using a gradient. But isocratic is just same composition all through the run. While your stationary phase is a solid bonded, immobilized, or coated phase on a solid support, which makes up the column. The stationary phase or the column. The column is like everything. If you see HPLC column, it's like a rod, and it has the stationary phase inside. Okay, so that column, we call it the heart of chromatography. Since the name chromatography means separation, it means that where the separation occurs is the most important part of that system. So that's why we call the column the heart of chromatography. That's where your separation occurs. So what is bonded in your column, what is inside your stationary phase or your stationary phase itself, any analyte that is coming will now interact with the stationary phase based on what polarity. So if the stationary phase is non-polar, so if you have a mixture of polar and non-polar and semi-polar, so the non-polar will be staying longer while the polar, highly polar, will be going out faster. So you can see the affinity to the stationary phase will make those compounds to now be separated. So that's how the separation occurs in liquid chromatography. Your components of HPLC, we have 5, which the first one is your pump. The pump, don't worry, I will show you a pictorial representation of the HPLC. So the pump we have 2 types of pump. We have the binary and quaternary pump. Binary pump using 2 lines for the mobile phase, while quaternary pumps have possibility of using 4 lines for the mobile phase. While your injector, the next one is the injector, which is your sampler. So you have a manual sampler and an auto sampler. So the manual sampler, you have to be using a syringe to inject your sample. So every run, if I'm doing this sample A, I'll go and inject it. Once it's done, I'll come back. Then I want to do sample B. I'll come back, take it, inject it again. Wait for it. When it's done, I'll come back. So you have to stay all through if you're doing manual injection. But if you have your HPLC comes with an auto sampler, so you have everything. The only thing you need to do is to create a sequence in your software. Place everything in the auto sampler. The auto sampler has capability of taking up to 100 to 150 samples, depending on the make of the HPLC. So once you can maybe have 50 samples, you can all prepare them, put them in your vials, then place them in the auto sampler. Then you can now program it in your system and say, okay, follow them, analyze them sequentially using this method. So once you send it, it starts running. You can go and sleep. Once it's done, you come back. Your result is ready. You analyze your result, get all your data, and you go. So it's very easy, very convenient for people to use compared to the manual. Then the column oven consists of a thermostated oven and the column compartments where you put the column. So we have different types of columns that can be used depending on the method of analysis you are using. So there's what we call the C18 column. We have the C8 column. We have C4 column. We have amino column. We have phenyl column. We have helium column. There are various types for HPLC. So depending on what you're doing. So the method, if you have a method, it will tell you the column to use. Okay. Then the fourth one is your detector for signal producing. So these are some detectors that are available. We are going to discuss some of them later. Then data processor, which is your computer. So that's where the software is which controls the instrument. So this is a diagram for HPLC. So you can see the data processor, which is your computer. Then the top part, you see solvent mobile phase. This is a reservoir that contains your mobile phase. Then you can see the pump. So the pump is to draw up the mobile phase that will go through the system. Then it has a degasser. The degasser is the mobile phase. Sometimes water or those organic solvents will have gases in them or air. Yeah. So what the degasser does is to degas the solvent entirely and remove all the gases in your solvent. Those gases affect your chromatographic run, affect retention time. It affects the analysis completely. So you have to degas. So the system, these new model systems come with a degasser. But if your HPLC does not have a degasser, then you can now do what they call use an ultrasonic bath. So you just place the solvent you want to use, put it in the container and place it in ultrasonic bath. Then you sonicate, then to remove the gases. Then you can now place it. Then once you pump into your solvent, it comes to the switching valve. Then from the switching valve, it takes the solvents, then your samples are being injected there too, then they mix with your solvent, which is your mobile phase, remember? Then everything now comes to your column that contains the stationary phase. Then separation will occur in the column. Then each analyte that is coming out is going to the detector and is being detected. So as it comes out and goes to the detector, you now see a peak creating. Then if the next one comes out, you see another peak, so on and so forth. And that's the visual representation of a HPLC system. Then steps in analysis using chromatograph. First, you prepare, you have reference material, reference or analytical reference materials or reference standards that are high purity. You purchase them. So if it's for aflatoxin aflatoxin B1 you're doing, you purchase the aflatoxin B1 standard, and you prepare the standard at different concentration calibration levels. You can do 3 to 5 point calibration, and you run them through the system. Then you now create a calibration curve from the results you've gotten, and you now prepare your sample, then analyze through the system. Then from the results of your analysis of your sample, you can now quantify the analyte of interest, that the B1, using the calibration curve that has been created with the reference standard. Okay, so this is just a step that can be used in chromatography. So these are detectors in HPLC. We have the UV. I think these detectors, as we are going to see now, we have the UV detectors. The UV detector uses just the essence, I think, is just absorb light. It uses Beer-Lambert's law for analysis. So your analyte of interest, once it goes to the detector, if it's a UV detector you're using, the analyte will absorb light. So the rate at which it absorbs that light is called absorbance. So in Beer-Lambert's law, we remember that Beer-Lambert's law states that absorbance is directly proportional to concentration, as long as what the path length remains constant. So that means absorbance is directly proportional to concentration. So you see that the formula will tell you absorbance is equals to concentration times path length, and you can use an extinction coefficient. So this is what happens there. So if the analyte comes, it absorbs light. So the rate of absorbance is now used to reflect the concentration of the sample, of the analyte itself. So that's for UV. Then there's one we call evaporative light scattering detector. This detector involves measuring the amount of light scattered by the analyte. So once the analyte goes through this detector, it will, there's the light that is already charged up to produce. So the analyte scatters that light. So once it scatters the light, it now produces what they call photons, and those photons can now be detected using a photodiode. So this is how you analyze any analyte using this evaporative light scattering detector. Then we have the mass spectrometry detector, which is based on mass to charge ratio. We'll discuss that one more. Then refractive index detector. Refractive index, that one deals with the refraction of light. You understand? So the how light is being, that's the refraction of light as the analyte flows through the system. So it measures how light is being reflected. So if that occurs, then you can now quantify the analyte of interest. Then the fluorescence detector, it basically deals with fluorescent compounds that can fluoresce. So for a compound to be able to fluoresce, that compound should be a aliphatic or alicyclic hydrocarbons, or it has what we call conjugated double bonds, or they have aromatic compounds. So once those functional groups are available, the compound has the ability to fluoresce. So those functional groups, what they do is they excite shorter wavelengths energy. Then once they excite those shorter wavelength energy, then they now emit higher wavelength energy, which we now call fluorescence. So is that fluorescence that is now being detected, then we can now quantify the analyte with it. So for gas chromatography is simply separation techniques that are used to separate volatile compounds So any compound that is not volatile cannot be separated using a GC. So that's why you see GC is kind of restricted compared to what LC. LC is more robust. Even compounds that are volatile and non-volatile, LC can really easily analyze. But GC, it must be volatile because you're using gas as a carrier, as your mobile phase, as a carrier. So you can't just infuse liquid and make gas to carry liquid through the system. So that gas, that liquid, as you are, you prepare your sample, it will be in the form of a liquid, which are organic solvents that you use for extraction. Then you've extracted the analytes. So you have to vaporize that liquid. Then the vapor will now be picked up by the gas, then taken to the column for separation. So you can see separation in GC is achieved by the differences in properties and structures of each component, the size and affinity of each interaction with the stationary phase. These are components of GC. We have the carrier gas cylinder. So the gases that are used, it has to be a non-reactive or an inert gas, because you cannot be using a carrier gas just to pick an analyte. And if the gas is reactive, it will react to the analyte, change the composition of the analyte, create derivatives. So you have to use an inert gas. Inert gases are non-reactive or non-reactive gases. So this is the mobile phase. The gases are the mobile phase in GC. Then sampler, it also uses manual and auto sampling method. Then injector, it has an injector. The injector is, we have vaporization injectors, we have on-column injectors, we have programmable temperature vaporization. For the GCs, we do have, they are mostly programmable temperature vaporization. It means in the injector, that's where the vaporization occurs. I told you your samples are prepared in form of liquid. So the injector will have that temperature vaporization technique where the liquid comes, it will now heat it up and vaporize it. Then the carrier gas can now carry it into the column. So the column is another component. Mostly in GCs, we use capillary columns. And these are certain detectors that are used in GC. Then we have the data processor. So this is a diagram of the GC. So you can see by the left-hand side, you see the carrier gas. That's a regulator. It sends the gas into a trap. The trap has filters. So if there are any impurities in the gas, it will filter it out. And the pure gas will now come out and come to the inlet. You can see number 3 here, the inlet. This space is your injector. So you can see your auto sampler will bring the sample as liquid. Then it will come to that inlet, which is your injector. So that's where your programmable temperature vaporization occurs. Then it will heat up the injector. Once it heats up the injector, then the injector will vaporize the sample. Then once the sample is being vaporized, the carrier gas picks the vapor, then goes through the column. Then the separation occurs in the column. Then it goes to the detector and detected, and you see your chromatogram. Simple representation of GC. Then detectors are in GC. We have the flame ionization detectors, which measures current from ions and electrons generated from ignition of analytes and mixture of hydrogen and air. And you have your electron capture detectors. These nitrogen carrier gas is ionized by beta rays, and the electrons released are captured by your electrophilic compounds, and resulting to these ions that are conductive, and the change in current results to peaks. Then your flame photometric detector are mainly for sulfur and phosphor containing compounds. Then your mass spectrometer. So your mass spectrometry is a technique that measures the spectrum of masses. Ionized molecules give positive or negative charge. So the mode of action of the instrument is driven by what we call the mass to charge ratio. I'll explain that. So you can see here, we have some components of the mass spectrometer. First is the ion source. The ion source, this is, the mass spectrometer is the entire detector. But inside the mass spectrometer, we have the ion source, we have the mass analyzer, and we have the detector itself, which are all components of your mass spectrometer detector. So for the ion source, we have different types of ion source depending on the system. EI is electron impact. ESI is electrospray ionization. CI is chemical ionization. APCI is atmospheric pressure chemical ionization. So these are different forms of ionization that occur. And EI and CI are the ones that are found mostly in gas chromatography. Why is ESI, APCI, there are some other ones, they call them MALDI. They are all found in LC, that's liquid chromatography mass spectrometers. So I will explain just the EI so that you understand how the mass spec occurs. What happens is you use either your GC to run separation of analytes. So once your analytes have been separated in the column, they are going to the detector. Let's say the first analyte enters the detector. What happens is that the EI, in the ion source, there's what they call a filament. The filament produces electrons. So those electrons will now bombard the coming analyte, the analyte that goes into the solid, it will now bombard it. So if it bombards the analyte, the electrons, the analyte will now lose protons. Thereby, you see a dissociation. So the what we call fragmentation, the analyte will fragment into different components, into different pieces. It can be 2, 3, 4, 5, depending on how the impact of bombardment of the electrons is to the analyte. So once that fragments occur, you see that whole analyte will now fragment. So if it fragments, those fragments will now be either positively or negatively charged. So that's why you see, we say ionization molecules giving positive or negatively charged. Then once these fragments are being created, those fragments will now go into the mass analyzer, which is the next part. In the mass analyzer, we have a single quad. A single quad is called quadrupole. These are like poles. They are just 4 poles. Quad, means 4. So 4 poles of positive, negative, positive, negative. So those 4 poles, one of it is a single quad. So if you hear the name GCMS, GCMS means 1 ms. That means that GCMS contains a single quad. Then if you hear GCMS-MS, that means you see 2 ms. But that ms, that GCMS-MS now contains what we call a triple quad. Triple quad, it has one single quad in the first ms. Then there's a chamber that contains some quads again. Then the second ms has another quad. So that's why they call it triple quad. So this mass analyzer, what they do is they analyze the masses. You've already fragmented with your ion source. Yes, bombardment fragments are created that are charged. So now the mass analyzer, the lower ions, that's based on their molecular, the fragments are created, the one that has the least molecular weight will now be channeled through that single quadruple. So it will now go, then followed by the next one. So it will move according to their masses. So that's why you see here, we say the mode of action of the instrument is driven by what we call the mass to charge ratio. So once they are being passed through the mass analyzer based on their masses, they are already charged. Then they now go into the detector, which we use a photomultiplier or electron multiplier. Then it now detects and now create what we call a mass spectrum. So you will now see that we say mass spectrometry is detecting a major spectrum of masses. So for that particular analyte that have been fragmented, you now see you see all the fragments as a spectrum. So once you get that spectrum, you keep it. So if you are doing what we call an unknown, and there's what we call unknown and known analysis. That means unknown, I don't know what I'm looking for. I just want to analyze this sample and just see what is it. You have a food sample, you want to run, you've extracted, you want to just run and see what compounds are there. That's unknown. But known, okay, this is my target. I have a target. This is what I'm looking for. You understand? Then you have the standard, then you now quantify. But for unknown, this EI GCMS is very, very good because the system comes with a library. The library contains millions of spectrums of different analytes. So if you have created your analyte that's gone through and has created that spectrum, what you do, you just take that spectrum that's been created, then take it to the library and compare. You do what they call a similarity search. Then you compare with the millions of analytes, spectrum that are in the library. So it will now scan through the library and compare your own spectrum and those in the library. Then it will now give you a match, a list of match. Then you can now see something and say, this one is 99%. It will show you 99% match to this. So you can now see the name of what is matching. So you show, if you have a 99% match, you are good. So the least criteria is 80%. So if you have an 80% match, you are good. You are almost certain that that is the compound you are looking for. So you see the molecular weight of the compound and the structural formula of the compound. So this is how a typical GCMS happens. Then your AS and ICP-OES, these are meant. So in your GCMS and LCMS and HPLC, for mycotoxins can be analyzed. That's aflatoxin, ochratoxins, and also can be analyzed with LCMS and HPLC. Like aflatoxins B1, B2, G1, and G2 can be analyzed using LCMS-MS, then can also be analyzed using HPLC that has a fluorescence detector. Then ochratoxins can be analyzed with HPLC that has a UV detector and can be analyzed with LCMS-MS. So all mycotoxins can be analyzed with LCMS-MS, but not all can be analyzed with HPLC. Okay. Then your pesticide residues can be analyzed with both GCMS, GCMS-MS, LCMS-MS. But your pesticide residues are hardly analyzed with HPLC that has a UV or a fluorescence detector or RI detector or whatsoever, but it can be analyzed with the one that has a mass spec detector. So GCMS, LCMS, you can do PESA residue. Then for your heavy metals, even your binary drug residues is LCMS and HPLC2. Okay. Then your heavy metals cannot be analyzed with your AS, which is your atomic absorption spectrometer, and also your ICP-OAS, which is your inductive coupled plasma optical emission spectrometer. The difference between these two is just your AS use absorption technique to measure your metal ion, your metal, while your ICP use an emission technique. So you can see they say AS, the instrument runs the test separately, and each halo cathode lamp emits its light, and the absorption is measured for a single element. So with the AS, you can only analyze a single element at a time. You have to get a lamp. Magnesium has its lamp. So once you want to do magnesium, you now put magnesium lamp in your AS, then run your samples. Then if you want to do sodium, you change it, put sodium lamp, run your sample. But for ICP, it has a universal lamp. It's not a lamp, so it's like a diode box, a universal one, that since you are not measuring absorbance, you are now measuring emission. Okay, so you can now run multi elements using an ICP. So ICP is the recent one. It's very wonderful to use. So you can analyze a lot of metals at once in the sample using your ICP. Okay, and in conclusion, food contaminants are a huge concern to the food value chain. As such, these contaminants need to be properly regulated and analyzed. Analytical methods are to be constantly improved. And as well, the competency of laboratory analysts should be a priority. We, as food safety experts, are key drivers in ensuring food security. Thank you for listening.
Wow. Thank you so much, Jerry. This is like, I just feel you should give all of us a certificate already, because I feel like we've had all the training needed in food safety.
Just a certificate course.
Oh, I'm serious, you deserve one. Wow, this is very exhausting. Like, it's covered everything. Thank you so much. Thank you for your time and everything.
You're welcome.
Yeah, just to be fast about this, I'm just checking if anyone has a question or something.
Okay, I think I have a comment and a little bit of a clarification of clarity. Anyone?
Okay.
Prof, well done.
Yes, Prof.
Hold on, that was an awesome presentation, Sanu.
Yeah, thank you.
I wanted to ask, because I knew there was some time ago that I made a presentation, and I was proposing a software that will allow more like a qualitative analysis, or a software that would detect the presence of food hazards.
Okay.
And I can remember that a professor who was there kicked against that and said that at the end of the day, he just gave a whole of a bad critics, you understand? So that's my proposal. But Misha, we're waiting on you now. I can't stand it. So I think from what you have, from your explanation and your presentations today, I think I see that it's something that is feasible, is achievable, just to work on. So thank you for that. And one more, a question just ran into my head. Talking about what is it called? Detection of aflatoxin, like you made mention of the mold growth.
Yeah.
I want to ask, is there any other characteristics, so to say, to use that could be used to find out if there is aflatoxin in a food product, so to say, aside mold growth?
Okay, that's a physical examination.
Physical examination, yeah.
Yeah. Okay, no, mostly, since aflatoxins aren't things that you see. You understand? They are toxins already, they are chemicals. You don't just see them. But the only thing is that you might even see a food that does not contain, that the mold is not visible, but it has mycotoxins, because it might be there, it might be cleaned up, but the toxins have already been produced. So, but you cannot, I don't think there's any other technique that you can visualize and say, okay, yeah, mycotoxin is present in this food. So, but seeing mold, there's this high probability that these toxins have been produced. But I'm not saying necessary that mold represents that. If you see mold that is compulsory, there's mycotoxins. You understand? Okay. You remember there was a statement I said, all mycotoxins are produced by fungi.
Okay.
You understand? All mycotoxins are produced by fungal origin, but not all toxins, not all fungal origin produces like other toxins. So you can see that there are some other toxins that are there that are not mycotoxins that are produced by fungi too. Yeah, they might not be mycotoxins, okay? So seeing a mold does not mean that it's mycotoxin itself.
Okay.
But it's just that it represents or show you that there's a probability that mycotoxins have already been produced in that food.
Okay. Okay. Yeah. The reason why I'm asking is that, okay, like,
okay.
you know, I'm a producer, a food processor.
Yeah.
And when I go to procure my raw material, because I see that the number one food that you mentioned, that this happened to be a raw material I use in my production. So I was kind of trying to find out, okay, the things I have to check out for when I'm actually procuring my raw materials. You understand?
Okay.
So that was
okay. I understand.
Yeah. Well, thank you.
Okay. All right. No problem.
Sorry, a quick one. I actually have two questions. The first one is like you talked about the vet's drug residues, and that's actually like an interesting one, which is like a bit new to me. So I was wondering, like, since you talked about all those antibiotics they give to them, which might actually like maybe cause drug resistance in our own body, is there like other methods like maybe proposed to farmers to use instead of like maybe using those medications?
Okay. Are you done with the two questions?
No, and then the second question I have to ask is about like, I can remember maybe when you buy, well, it's part of the question Ima asked though, like when he said like the fungus stuff, like I'm just going to give an instance, like maybe you have a bread and then like mold is growing by the side of it. I know like maybe when we were younger, we just have this habit of maybe just removing the side because it's like not inside and then we eat it. But then hearing you talk about not all fungus being mycotoxin, I don't know how you said that. So is it that, oh, it's really not too bad because it might be like no mycotoxin is actually in the bread, it's just like a fungi growth? I don't know if you get what I'm asking.
Okay, can you rephrase that question? Sorry.
Okay, so I'm saying like as a child, we had like this habit, like, you know, when you buy your bread and then it stays over time, right? And then you have like mold growing by the side, like it's on the outside, but not on the inside. Like, so we're like, oh, it's just on the outside, and then we remove it and then we eat it. But then when you talked about not all fungi growths like produces mycotoxin or something like that. So is it like it's not really a bad practice because then it might be that it's just the fungi growth, not that there is mycotoxin present in the bread?
Oh, okay. All right, let me start from the last one. It's possible because, the statement I made the other time is all mycotoxins are from fungi origin, but not all toxic compounds produced by fungi are mycotoxins. You understand?
Okay.
Yeah. So all mycotoxins are from fungi. So any mycotoxin that you see is from a fungi origin. But fungi also produce other toxins that are not termed mycotoxins.
Okay, I get what you mean.
So that's it. So even those things, the bread, seeing maybe mold in bread, that's why I told you there's a probability, once you see mold or fungi infestation in those kind of products, there's a probability that those mycotoxins or any other toxic compounds have already been produced because it's part of their replication system. You understand?
Yeah.
As they are doing that, they are replicating, they are producing some other byproducts. Those byproducts are the toxins. You understand? Part of the way they live in that substance. So they constantly produce some byproducts. So those byproducts are the toxins. So you can see a mold or a fungal infestation. But you notice that during the course of the presentation, there were specific organisms that produces certain type of mycotoxins.
Yeah.
You understand? Like aflatoxin, I was talking about aspergillus, flavus, and parasiticus. Ochratoxins, I was talking about aspergillus, ochrasius, and penicillium. You understand? So if those organisms are mostly fungi. So if they are not the specific organisms in that mold of fungi you are seeing, then they might not be producing those mycotoxins. You're thinking.
That makes perfect sense. Thank you.
Yes. Then the first question was regarding veterinary drug residues and if there are other proposed substances that can be used by farmers instead of the drugs, right? Yeah. So for that, sometimes it might be difficult because, for instance, you're having a poultry farm and your chickens are having cold. So it's sometimes very difficult to just get an alternative medicine, except you're trying to go into herbal. You understand? Which you are not sure it might affect the chicken. You're not sure some other toxic properties that are in the herbal preparation. So all these factors, the drugs are the most possible things to use to treat those ailments. So what you use the drug for is just for treatment, to treat. You understand?
Yeah.
So, well, at the same time as we are treating, unfortunately we are leaving some of those drugs in the animal products. It's unfortunate, but sometimes you just have to treat. So, like, I've seen some farmers coming up, some poultry farmers especially, there are certain type of sickness that they are required to use certain drugs to treat. But I've seen some using bitter leaf, using zobo.
Ginger, garlic,
Ginger, garlic, and especially when they're having cough, you see they mix up, instead of giving them the drugs, they just mix those natural products and give them, and it works. So these are alternative substances that can be used instead of the drugs.
That makes perfect sense. Okay, thank you so much. Thank you.
All right, you're welcome.
Okay, sorry, any other question? Well, in the absence of that, I would like to say thank you so much, Jerry, for your time and everything. This was very engaging. And then for everyone present, it's really nice to have you all here. And good night, all.
All right, good night.